it's starting.
Ania, już.
Okay. Hello, everyone. It's my great pleasure to welcome our next invited speaker, Professor Gianna Sasaki Nobrega. She is a professor at the Department of Applied Mathematics of the University of Rio de Janeiro in Brazil. Earlier, she was connected with another university there, namely with the Federal University of Rio de Janeiro, where she graduated her bachelor degree and PhD degree. First time we met in one of conferences in France. I think it was in Grenoble in conference during her state postdoc position. There with the in the group of very well-known Professor Miriam Preissman, also connected with total coloring, because the main interest of Gianna is connected with total coloring of graphs. I think there is also one very interesting point in her CV, namely she awarded L'Oréal Prize for Women in Science. I must admit that you are the first mathematician who I know who awarded this prize, because it's not usual to the mathematician receive this kind of award. So even more congratulations. Now Gianna is going to present us her result connected with total coloring. And now, Gianna, it's your time. Please welcome.
Thank you, Hannah, very much for the invitation. I'm very happy to be here. And so I'll try to present you some results about total coloring of cubic graphs. So,
okay.
Is it okay?
Yeah,
okay.
We are able to see. Yeah.
So thank you for the presentation. And my name is Gianna. I'm from Rio de Janeiro. And first, I introduce total coloring, edge coloring, snarks. And after, I start to present our results about type 2 snarks and type 1 cubic graphs, and so on. So first, an edge coloring is an assignment of colors to the edges of a graph so that adjacent edges have different colors. And the famous Wiesen's theorem states that the chromatic index of a graph is at least delta and at most delta plus 1, where delta is the maximum degree of a graph. And because of this theorem, we can have a classification of simple graphs. And so more specifically, for cubic graphs, we have that cubic graphs with chromatic index equal to 3 are said to be class 1. Otherwise, they are said to be class 2. Okay, here we have two examples. The first one is the K4. And the K4, we have a 3 edge coloring, so the edges can be colored with only 3 colors. Okay, but here we have the well-known Petersen graph, and we cannot have a 3 edge coloring for this graph. It needed 4 colors. Okay, so in a similar way, we have total colorings. And so a total coloring is an assignment of colors to the elements, edges, and vertices of a graph so that adjacent or incident elements have different colors. Okay, and we have not a theorem, we have the total coloring conjecture from Wiesen, due to Wiesen and Bézat, which states that the total chromatic number, at least number, is the least number for which a graph G has a total coloring. And the total chromatic number is at least delta plus 1 and at most delta plus 2. And it's not difficult to see the bound delta plus 1, because if you have a cubic graph, all vertices have degree 3, but suppose a vertex with maximum degree of your graph. So we need delta colors to color the edges, the incident edges, and one more color to this vertex. Okay, and this conjecture has been proved for cubic graphs, and so we have a classification here, and cubic graphs with total chromatic number equal to 4 are said to be type 1. Otherwise, so the total chromatic number equal to 5 are said to be type 2. Okay, here we have the same two examples, but now the Peterson graph we can color with 4 colors in a total column, but the K4 we cannot. So the K4 it needs 5 colors. Okay. So I present just the same examples here with an edge column and the side and a total column the other side. Okay, they are all cubic graphs. And now I start to present the class, a special class of cubic graphs, namely SNARKs. And so before I present you the four color conjecture, and the four color conjecture states that no more than 4 colors are required to color the regions of a map, so that no two adjacent regions have the same color. We have here an example, a nice example. And in 1880, the four color theorem was proved to be equivalent to the statement that every cubic breachless planar graphs class 1. So SNARKs were defined in this context. This name was given by Martin Gardner based on the poem of Lewis Carroll, The Hunt of the Snark, because there a snark was an animal very difficult to find. So this name is because of this poem. And so SNARKs are class 2 breachless cubic graphs. Okay, and the earliest and the smallest one is the Peterson graph. Okay, here you have the Peterson graph in this example. But why did we decide to consider total coloring of SNARKs or total coloring of cubic graphs? So first in 2003, Cavicula and co-authors verified that all SNARKs with girth at least 5 and fewer than 30 vertices were type 1. After that, in 2011, Brinkman and co-authors verified that all SNARKs with such girth, which means girth at least 5 and fewer than 38 vertices, are type 1. So they proved it by using the computer. Okay, but later on, Campos, Dantas, Simone Dantas, and De Mello proved that all members of two infinite families of SNARKs, so Flower and Goldberg, all members are type 1, and we started to investigate this class of SNARKs, and we proved that both Blanusa families and Lupicini families are type 1, all members of these 3 families. Okay, and in the same paper in 2003, Caviculi and the co-authors proposed a question about cubic SNARKs with girth at least 5 and type 2. So the question one is there any type 2 SNARK with girth at least 5? Until now, we could not answer this question, but we have some results relation to this question, okay? And we decided to propose by investigating this class of snarks and also cubic graphs, we decided to propose other two questions. Question two is there any type 2 cubic graph with graph at least 5, not snark, in general, cubic graphs with graph at least 5? We don't know. And question three is about equitable total chromatic number, equitable total column. And is there any type 1 cubic graph with equitable total chromatic number 5 and graph at least 5? We think that there is a relationship between the total chromatic number and the equitable total chromatic number with regular graphs or cubic graphs and the graph of the graph, but we cannot see this relationship yet, okay? But I think maybe we can try to find some relation. So now I start to present to you some contribution to question one and question two and question three. And before some useful definitions. So a semigraph is a graph, and we can have edges, semi-edges, which are edges with only one endpoint. Okay, here we have an example. We are interested in cubic semigraphs. So in general, we have or a cubic graphs, either cubic graphs or a cubic semigraphs. So we have 4 semi-edges, almost always, okay? And a junction, so if you have 2 semigraphs with 4 semi-edges, each one, so the junction between these 2 semigraphs is the connection, is a graph, is any graph that you can obtain by connecting these 4 semi-edges, okay? And the first result I present to you is a type 2, the first type 2 snarks we could found. So they have 40 vertices, okay? And the construction of these snarks was a collaboration with Professor Miriam Presman from Grenoble and also Professor Gunnar Brinkmann from Ghent. Okay, and we could find this brick. Okay, this brick that is class 2, and this other brick which is type 2. And so, but we can see here that this brick has a lot of squares. Okay, has a girth 4. It's not the snark we have constructed. They have girth 4, and so we cannot answer Cavicchioli's question, but we could present the first type 2 snarks in the literature. And so here we have this snark, okay? So this graph is a snark, and it is type 2 with 40 vertices, and we have 11 snarks with 40 vertices that are type 2, okay? It was found, especially this part, this blue part, this blue brick, was found by using the computer. Okay, and so after this first result, we investigated the second question about type 2 cubic graphs, not snarks anymore. And we have that all known examples of type 2 cubic graphs contain triangle or squares. That's funny because we don't know a type 2 cubic graph with girth at least 5. Okay, here we have the example. This graph is the generalized Petersen graph G51. So this graph has 10 vertices. This graph is type 2, is cubic, but it has squares. So it has a girth 4. And we started to investigate this class of graphs, the generalized Petersen graphs, to understand more about this relationship. Okay, so and the generalized Petersen graphs are graphs that consists on a set of external vertices in a cycle and a copies of these vertices in a inner cycle, okay? Or in fact, we have in the inner part we have the distance. That the distance between these vertices are relevant, okay? So this graph, for instance, is the G51, and this one is G93. 5 and 9 because of the number of vertices in each cycle, okay? And the 1 is because of the distance between the inner vertices. So here we have distance 1, V0 to V1, V1 to V2, etc. And 3 because V0 to V3, so 1, 2, 3, and so on, okay? They are the generalized Petersen graphs. And we could prove, we could find total colors with delta plus 1 colors to an infinite families of in this class of graphs, okay? So it's a contribution because we cannot find any type 2 in this family, but we know that G51 and G93, they are type 2, but our result is about type 1 graphs in this family, okay? So, and the construction of these colors is in the following way. So we have two pieces of a generalized Petersen graph, and to semi-graphs, in fact. And so we have by doing the connection between these edges, so we can construct a generalized Petersen graph. And we colored each part, each brick, to obtain without conflict a 4 total coloring of the resulting graph. So we make the connection between these edges. So of course the number of vertices will change. And so we have the G11-2, for instance, in this example. And we've tried to found a total coloring with the restrictions that semi-edges that will connect will have the same colors, and the end points of each one must have different colors, okay? And so we could do that in a similar way to obtain the 4 total columns of this class. And if we think about the number of vertices in each part, we can have a very nice corollary, because this theorem states that the generalized Petersen graph is type 1 for k at least 2, because k equal to 1, we know that they are all type 1 except for the G51. These results, I think, is due to Chetwind. I'm not sure now, but so we consider k at least 2, and for any such that n is 2 times k, and so we could find a total column of this part And of this part 2k minus 1, we constructed a four total columns of two parts. The first part was with 2k vertices, and the second one was with 2k minus 1 vertices. And so we have that we can copy a lot of copies as I want. So lambda and me to obtain an infinite class of graphs. So like that, and the columns must be compatible, and so we can obtain this infinitely many type 1 generalized Petersen graphs. And so the a very nice corollary. So we have that by Sylvester's formula, each integer n that as at least 2k minus 1, 2k minus 2 can be obtained as a combination of 2k and 2k minus 1. So we have that we have this corollary to uh, to 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 present that there are infinitely infinite families of generalized Petersen graphs that are type 1. Okay, and with Professor uh, Giuseppe Mazzuoccolo and from Italy, and Vinicius dos Santos from Minas Gerais in Brazil. So we could found by using the computer some other type 1 generalized Petersen graphs. And we have this theorem, for instance, all generalized Petersen graphs with k at most 6 are type 1, except for these two graphs that is known to be type 2. Another now another family we could establish the total column was the superposition family. Now about snarks again. So the superposition construction is due to Koshol, and the construction of these graphs is in the following way. So here we have the Petersen graph, okay, with another representation, not the usual representation, but here is the Petersen graphs, and so a snark. And the construction consists on we remove these external edges of the circle, and replace these outer vertices by this piece of vertex with semi-edges we'll call the vertices, okay? And we replace the edges that we removed by another piece of snark. So here we have 1, 2, 3, 4, 5, 6 copies of the flower snark by removing some elements from it, okay? And by connecting everything, we have another snark. And this snark has 118 vertices, and is the first snark of this family, because we can put here another flower snark with another number of verts, and we can make the same construction to obtain another snack. And so this result was obtained with again with Professor Miriam Pressman when I was in Grenoble, and we could determine four total columns for all graphs of this family, okay? And now I will present to you some studies about equitable total color. So just to remember, a total color is equitable if the cardinalities of any two-color class differ by at most one. Okay, sorry. And we have the conjecture, in this case, the equitable total coloring conjecture, which states that the equitable total chromatic number is at most delta plus 2, is similar to the total coloring conjecture, okay? And this conjecture has been proved for cubic graphs by Wang. And the question 3 is about the equitable total chromatic number of, in our case, cubic graphs, but maybe it's interesting to generalize to regular graphs. I have no idea, but it's about cubic graphs with that are type 1, because if a cubic graph is type 2, we know that we have an equitable total column with type 2, with delta plus 2 colors. But if you have a cubic graph that is type 1, the question is good, because maybe we can have equitable total column with delta plus 1, but maybe we cannot have, and so we have a equitable total column with delta plus 2 colors. Okay, so the question is relevant. And although there were no examples of graphs such that we have this difference between the total chromatic number and the equitable total chromatic number, none of them was cubic. So here we have an example. And in this example, we have a lot of triangles. Okay, so we have a small girth. So we are still looking for a cubic graph, a regular graph with a girth at least 5. Okay. So question 3, just to remember, is there any type 1 cubic graph with equitable total chromatic number 5 and girth at least 5? So we could present a family, an infinite family of type 1 cubic graphs with equitable total chromatic number 5. But what's the problem? The problem is that all these examples, all these graphs have girth 4, small girth. Okay, so it's a contribution, but we cannot answer this question. And so I I will present to you the construction of this family, because I think it's interesting, and maybe it's an idea to generalize the result. I don't know. Okay, so the construction is by using this semigraph. Okay, and this semigraph has a very nice property about for total color. So this is a cubic semigraph, in fact. So we have always degree 3 in this semigraph, and in all 4 total columns of this graph, these 3 vertices must have different colors, and these 3 semi-edges must have the same color. And that's the problem, because we will construct a family by using this semigraph, and so consider a cubic graph, any cubic graph. So we replace each vertex of this cubic graph, original cubic graph, by this semigraph K23, okay? So like that. And so because they have a special for total coloring, we can construct a for total coloring, but it is not equitable. Okay, so we have, and the proof is in the following way. So here we have we replace each semigraph by a triangle, so we can color the vertices of these triangles, and it is possible because of the Brooks theorem. And so, by replacing again by this semi-graph, we know that all four total columns must have these three vertices with different colors, and these edges here, now not anymore semi-edges, now we connect everything, so they must have the same color. So the same color, in this case, orange. And so we have a four total column, a nice four total column, but it's not equitable. So we have, and the construction of this family is in this, like in this example. And so we have that all these graphs are type 1, but they have equitable total chromatic number 5, and they have squares. So question 3 we could not answer yet. Okay, but as I said before, maybe we can try a relation between question 2 and question 3, because just remember question 2, so is there any type 2 cubic graph with graph at least 5? And question 3, is there any type 1 cubic graph with equitable total chromatic number 5 and the graph at least 5? So this question are related each other, because the examples of the first known type 1 cubic graphs with equitable total chromatic number used this semi-graph special with special for total colorings. Okay, indeed, is the graph K23 we used from the small graph type 2 K33 by removing a vertex. So just to, so this one is obtained by the K33 by removing a vertex. And we know that the K33 is type 2, so maybe we can construct another semi-graph with graph at least 5, and so maybe a positive answer so to question 2 about type 2 cubic graph with graph at least 5, maybe we can construct a semi-graph to obtain a positive answer to question 3 about a large graph type 2 cubic graph with equitable total chromatic number 5. Maybe it's possible. We don't know yet. Okay? So about generalized Petersen graphs, we have some partial results about equitable total chromatic number 4. So for every n, at least 4, the generalized Petersen graph GN2 has equitable total chromatic number 4, and we have the other theorem here for any at least 3 and different from 5, the generalized Petersen graph GN1 has equitable total chromatic number 4. So maybe it's interesting to consider the equitable total chromatic number of generalized Petersen graphs, but we didn't try a lot. Okay. So now a recent research we've presented yesterday in another conference here in Brazil. So we could prove that we could find equitable four total columns of two infinite families of snarks and a part of Lupkini family, just some members, and all members of this blow up family. Okay, another family of snarks. So they have equitable total chromatic number 4. Here we have an example, just one example of the blow up member of the blow up family, and with an equitable for total coloring. Okay. And here, just the main references. And the first one is the paper with the first type 2 snacks we could found with Brinkman and Prasmo. And here, the third one is the Cavicchione and the others Italian co-authors, and with the motivation of this work because of the question about type 2 snack with a large girth. Okay, so that's it. I finished now. I hope we could enjoy. Thank you very much. Muito obrigada. That's it.
Okay, thank you very much, Diana, for your interesting talk. Now it's a time for questions, remarks. I think we have to wait for questions. People can write on Facebook and on YouTube channel, and we will see. But I have some questions to you. First one, you are focusing on finding type 1 graphs in the sense of total proper coloring or total equitable coloring. Yes, classical or equitable with big girth, yes?
Yes.
But what is your experience? Majority of cubic graphs are of type 1 or type 2, according to graphs?
I think we can prove that they are all type 1, but and I think
No.
Miriam thinks the same, but we don't know.
No. Do you think that all cubic graphs of big
With
girth
girth,
girth are of type 1?
yes,
Okay.
yes, but I
Yeah,
don't know.
yeah, of course. Yeah, it's only conjecture,
What do
but
you
very
think?
interesting.
What do you think? Can you
About what?
cubic graphs with girth at least 5?
I didn't
Do you
consider
have
this
an
problem.
idea? No? Yeah, okay.
Yeah, but we also, me and Rita, we were considering equitable total coloring
Yes,
about coronas of cubic graphs. And there was, of course, the product, the corona graph is not a cubic. But
okay.
our result was that independently on the type of cubic graphs, the corona of cubic graphs is always type 1. But it's first of all, it's not a cubic graph,
yes,
corona.
yes.
And secondly, now as I considering the girth of this graph, corona has always girth 3, so it's a small.
You see, that's strange.
Yeah. So it's an example of a graph with small girth and
Yes.
of type 1. Yes. But you also mentioned about Peterson graphs, modified, generalized. Yes, generalized Peterson graph. They're also cubic. Yes, because I don't catch the definition.
Yes.
I didn't catch the definition.
They
It's
are
a
all
cubic graph,
graphs. Yes.
but okay, but there is also a small degree, small girth, yes, of Peterson graph.
Not all, and we have many generalized Peterson graphs with girth 5 and 6, etc.
Okay, but they are of type 2.
Type 1.
Type 1.
Yes. Only two, only G51 and G93 are type 2 until now.
Okay. As I remember, it was probably your result that deciding which value of total chromatic number is correct for cubic graphs is NP-complete problems. Yes, it was in your paper. Yeah, with Prisman, with Miriam. Yes.
Yes.
Yeah, because deciding which graphs of type 1 are graphs of big graph is another problem.
Yes.
Yeah. Could you recall the first question?
Yes, of
Who
course.
posted this question?
Can I share
It's almost 20 years
again?
ago, yes?
Yes. 2003.
Yeah.
So
It's also about cubic graphs, yes? It was question one about
in fact, about snarks.
snarks.
Here, yes, about snarks. In this paper, it was a survey, a kind of survey about snarks, only about snarks.
Yeah.
And so,
yeah, because
yeah.
The first two questions ask about graphs of type 2 with big graph. Yes, but the question 3 is quite opposite because it's about cubic graphs but type 1.
Yes. Cubic graphs with type 1 with girth at least 5 we know, a lot of. But with equitable totochromatic number 5, no, not yet.
Okay. Okay. Because it's equitable type 2.
Yeah.
Equitable because 5
equitable
it means type 2.
Yes.
Okay.
Yes.
Okay.
Always about type 2. Total column or equitable total column, yes.
Yeah.
Very
Now I understand.
Questions, I think, yes.
Okay.
But I think it's interesting.
Yeah.
I don't know.
It looks very simple. Simple because the formula of this those questions are clear, but the answer is not simple. Okay. Do we have more questions? Yeah.
We don't have more questions.
Julian, could you help me? Do we have some comments, questions?
We have a lot of comments. Everything was very nice and full of colors.
Very nice pictures.
I like total coloring.
Thanks to you for the interesting topic and many colors.
Thank you.
It was a very nice talk. Vinicius says bravo.
Bravo.
On Facebook, Rihanna says, thanks, Diana. This was a really interesting talk.
Thank you.
And let me check. I think those are all the comments that have arrived right now. It was a really nice talk.
Okay.
So thank you, Diana, once again. Maybe somebody from organizing committee have some questions, remarks.
Well, I have a remark.
Yeah.
Remember, everyone, that for the videos of the contributed talks of tomorrow will be uploaded before Paulina's talk, so that we end the event at Paulina's talk. That's all the information.
Okay. So, Diana, thanks again. We have one custom. Rita is announcing this custom.
I just like to say, Diana, thank you very much for the talk.
Thank you.
And I am very happy that Card was your, I don't know, godfather, something like this, in this talk in English. So congratulations. Thank you very much.
Thank you. Thank you again.
Okay. And our custom is, Rita, that the invited speaker says something in their native language.
So it's like, see you tomorrow and thanks a lot.
Anything that you like to say in Portuguese.
Em português?
Yes.
Yeah.
Your native
Yeah.
English, yes.
I don't know.
You
What
may
can I
invite us
say?
for. Yeah, you may invite for the tomorrow last day of the conference.
Ok, então tenho o prazer de convidá-los para o último dia da conferência CART, em português CART, I don't know. CART. Não faltem,
Okay.
venham todos, será muito legal.
Okay. We believe that it was
nice.
exactly that.
Did you understand, Juliana?
No.
Rita? No?
A little.
A little, a little.
Okay.
Yes, Spanish.
Because
My
Portuguese
accent.
and Spanish are quite close. I don't
Yeah.
know. Am I wrong?
I can understand something.
It was not necessary to understand, but look at you.
Yeah.
Okay, it's okay.
I think that
Thank
in
you.
general, the people that speak Portuguese understand better Spanish.
Yes.
The people that speak
Okay.
Spanish understand Portuguese.
Okay.
Yeah, maybe.
Okay.
I can understand you. I think so.
Ok. Muy bien,
Mhm.
muchas gracias.
Muito obrigada, muito obrigada.
Muchas gracias.
Okay. So thank you very much for today, and to see you tomorrow, every one of you. Bye.
Ok, bye.
Bye.
Hasta
Bye
mañana.
bye. Ciao.
Muchas gracias,
Ciao.
Diana. Bye bye.